Video 1, Physical Quantities and Estimation. Here is the sequence of the slides. Slides 1 through 3 explain how physical quantities in physics are represented. Slides 4 and 5 provide a list of physical quantities with corresponding units. Slide 6 provide a list of estimated values of physical quantities. And slides 7 through 10 show worked solutions about estimation for the AS Physics Past questions listed below. How to represent values in physics? Physics is a science that converts observations into numerical values to calculate powerful information for real-life applications. For this reason, physics quantities use a standard format that can be read and interpreted by anyone. In physics, all quantities consist of a number and a letter or letters from Latin and Greek alphabet. The number indicates the amount and the letter is related to the type of measuring instrument used to determine the number, which we call unit. To keep this explanation simple, try this. Obtain a ruler and a pen or pencil. Place your pen or pencil at the 0 mark on the ruler with the centimeter side. Here is an illustration. Read the length of the pen. In my case, in this picture, I see approximately 14 centimeters. 14 is the value and centimeter is the unit measured. Because I'm measuring how long is the pen, we say this way: the length of the pen is 14 centimeters. To write physics quantities, instead of the length of the pen is 14 centimeters, another letter, again from the Latin or Greek alphabet, is assigned to represent the sentence. Example, replace this sentence, the length of the pen is 14 centimeters, with the format L equal to 14 centimeters. As you see, the letter L in this case replaces the whole sentence, the length of. This assigned letter to represent the length of the pen is called physical quantity. Writing physical quantities is very useful for calculations to present results in a sequence that anyone can follow and understand. In conclusion, in physics, quantities are represented by an assigned letter followed by the equal sign, a number, and a unit letter. Like, for example, L is equal 14 centimeters. The confusing part of measuring in physics is that sometimes the same letter represents the quantity and the unit. An example, the letter V be used to represent the physical quantity of velocity, volume, or voltage. So here are the quantities, and all of them, velocity, volume, and voltage, are represented by the letter V. Now the units for velocity is meters per second. The unit for volume is cubic meter, and the unit for voltage is also the letter V, but in this case represents volts. Another example. In this table, the letter M has different meanings. For example, quantity, here we have mass, that is represented by the letter M, and the unit is kilograms. The meter, also represented by the letter M, but now M is the unit for length in meter. Now milli, which is a prefix, is also represented by the letter M, indicates a multiplier, which is 10 to the negative 3. Here is a table with common physics quantities using physics with the symbol, common units, and example on how to write using the symbol, the equal sign, the numerical value, and a unit. So here we have, for example, for length, letter L, common units, meter, centimeters, millimeter. For mass, lowercase m, common units, kilograms and grams. Temperature, uppercase T, degree Celsius, degree Fahrenheit, or Kelvin. For volume, the letter V, cubic meter, cubic centimeter, cubic millimeter. Area, uppercase A, square meter, square centimeters, square millimeter. Speed or velocity, S for speed, velocity is V. The unit, meters per second. Density, use the Greek letter rho. And the units for density is a derived unit. So here we have kilograms over cubic meter, or grams over cubic centimeters. Acceleration, represented by the letter A, meters per second square. Here we have 3 different types of energy, and in this case we use subscripts. For example, E sub P for potential energy, E sub K for kinetic energy, and E sub E for elastic energy. So the unit for energy is joules, represented by the uppercase J. Force, tension, friction, drag force, they are all force. But sometimes they have different symbols. For example, force is F, uppercase F. Tension is a force in cables, ropes, chain, strings. So it's represented by the uppercase T. It also is a force. And the unit for force is Newton. So like you see, Joule, Newton, they are scientists' last names. So they use the first letter to represent this quantity. Okay, so friction and drag force. So you can use the F with an abbreviation, F sub F for friction force, F sub D for drag force. Moment is represented by the Greek letter tau. The unit is Newton meter. Momentum is represented by lowercase p, and the unit is kilograms times meters per second. Here in slide 5, we have another table. Is the same, is with quantities, symbol, and common units. For time, period. So period here is uppercase T, but period also is a quantity that represents time. So the units are second for time and period. Frequency, hertz. Wavelength is represented by Greek letter lambda. The unit is meter, most meter, centimeter, just an example. Resistance is represented by, the unit is represented by the Greek letter omega. Resistivity is represented by the Greek letter rho. Voltage V again. So you saw previously the letter V being used for also speed. This V, and also units for voltage, which is volts, is also V. Current, uppercase I, the units is ampere or uppercase A, amps. Power P, watts. Electric charge, lowercase q, coulomb. And the elementary charge is 1.6 times 10 to the minus 19 coulombs. Pressure is represented by the letter P, the units Pascal. Stress, sigma. Sigma here is the lowercase sigma. Uppercase sigma is a little bit different. Also the units Pascal. Strain, epsilon, does not have a unit. Young modules, uppercase E, the unit is Pascal. Now for questions related to estimation, you need to rely on knowing the units and from an educated guess. So this table can help with estimated values of a couple of things that you might see on your exam. For example, mass of a person, 70 kilograms. Height of a person, 1.5 meters. Mass of a car, 1,000 kilograms. Speed of sound in the air, 300 meters per second. Power of a light bulb, 60 watts. Mass of a proton, 10 to the negative 27 kilograms. Diameter of an atom, 10 to the negative 10 meter. Walking speed of a person, 1 meters per second. Speed of car on the road, 30 meters per second. Density of water, 1,000 kilograms per cubic meter. Weight of an apple, 1 Newton. Typical current in domestic appliance, 30 amps. EMF of a car battery, 12 volts. Volume of a can of a drink, like a soda can, 300 cubic centimeters. Now, in slides 7 through 10, I'm going over 4 questions from AS Physics exam about estimation. So the first question, what is a reasonable estimate of the volume of an adult person? So your first thing is imagine a person and imagine some shape that you can work with. Let's say the shape of a rectangle, kind of, and a cylindrical shape. Now, according to our estimation table, we can say that the height of a person is 1.5 meter. Now we need to look at, to find the volume of those shape, you need to look at the cross-sectional area for this, let's say the rectangle. Let's say that you have like 2 feet side by side here. If you're standing up, you have your 2 feet. And here we are gonna have like a circular shape, kind of. So in this case, we are going to estimate that the length that of a foot is about 30 centimeters, like the size of one classroom tile. And let's make this a squarish one, and that will be also 30 centimeters. Now, what about the circular shape? In this circular shape, you can say that also the diameter is 30 centimeters. Okay, so now we have 2 different shapes, and we are going to have 2 different formulas for volume. So now the volume formula for a rectangle shape is the length times width times height. We have everything, yes we do. So, and what about the volume formula for the cylindrical shape? So we know that the volume is the cross-sectional area times the height. And the cross-sectional area, in this case, is circular, is pi r squared. Okay, so let's go back here to the rectangle shape. So we have 1.5 meter as the length or height, all right, the length. Actually, I changed a little bit the order, but its multiplication will not matter. So let's start with width and, okay, length and width. So 30, you have to multiply all those three values. 30 times 30 times 1.5. But you don't see this here. You see 0.3. The reason is because we need to convert 30 centimeters to meter. So you need to divide by 100, and we get 0.3 meter. So the result is 0.135 cubic meter because you are multiplying meter 3 times. Now let's go to see the cylindrical shape. Now we have the 30 centimeters here is the diameter. So the radius will be half of 30, which is 15 centimeters. Divided by 100 to convert to meter is 0.15. We need to square this times the height, which is 1.5. So the result is 0.106 cubic meter. So two different approaches, two different answers. However, let's look the options that we have for this question. The option here that we can play with will be option A, because there will not be 0.5, no 1, no 2. So A is the correct one. Now, slide 8, the second question is, what is a reasonable estimate of the kinetic energy of a car traveling at a speed of 30 meters per second? Couple things that we need to look. First off, is asking the kinetic energy. So in this case, we need to know the formula for the kinetic energy. And the other portion of information is the car is traveling. So the car is traveling, so must have a driver there. So we have to consider also the mass of the driver. And the information is given about the speed, which is 30 meters per second. So what is the kinetic energy formula? Is the mass in kilograms times velocity squared divided by 2. We have the velocity, we don't have the mass. So number one, we need to estimate. The estimated mass of a car is 1,000 kilograms. And the estimated mass of a driver or person is 70 kilograms. And the velocity was given, 30 meters per second. So now I'm going to make the substitution of all the numerical values in the formula for kinetic energy. So is, for the mass, is 1,000 plus 70 times 30 squared divided by 2. And the result is 481,500 joules. In scientific notation is 4.8 times 10 to the 5 joules. And why I did this? Because the results is not showing an exact number, it's showing the power of 10 value portion. So 4.8 times 10 to the 4. So definitely is not A, definitely is not D. So if you are looking, if you are struggling between B and C, so that is the way to think. You are estimating. Usually when we estimate, you go a little bit over the value. And if you opt for B, you'll be too low. If you opt to C, well, you'll be a little bit higher, but here we are, 4.8 times 10 to the 5. So I will choose the option C because it's estimating, so you have to go above the value. Now, slide 9 is showing the third problem, which this time asking to estimate the mass of a raindrop. That's tricky. There are lots of thoughts in this question. Let me start by picturing in my head a raindrop. So a raindrop is made of water, right? So if it's a raindrop, we can use the density of the water that we have in our table, on our estimation table that I gave you in this video, which is 1,000 kilograms per cubic meter. So the formula for density is mass. In this case, I'm using kilograms, volume, and cubic meter. So to calculate the volume of the raindrop, consider a spherical shape. So when you calculate volume, you need to determine the shape of the object. In this case, we are going to think of a sphere. And if it's a sphere, we are going to have a radius. But the question is, what is the radius of a raindrop? So let me bring here these marks here of a ruler and look at the marks. I don't want to go too small, and let me think about 1 millimeter if you be a reasonable size of a raindrop. Might be a little bit too big, but let's work with that one. So the estimated radius of a raindrop is 1 millimeter. Converting to meter, we divide by 1,000 is 0.001 meter. In scientific notation is 1 times 10 to the negative 3 meter. Okay, so now I'm going to use the formula for a sphere to calculate the volume of a sphere, which is 4/3 pi r, which is the radius, cube. So my radius is 1 times 10 to the negative 3 cube, and doing the calculation, and that's what I get. But that's not the answer. I'm looking for the mass. So now I need to do something. So this is the density formula, which is mass over volume. I'm using kilograms per cubic meter because that's how we start with. Now I'm going to rearrange this formula in terms of mass. So in terms of mass, will be the density times the volume, right? So the density is 1,000 kilograms per cubic meter times the volume that I just calculated. And when I do my multiplication, and that's the results that I get. But again, the options are just showing the power of 10 section of my value. So here is 10 to the minus 6, right? 10 to the minus 6. So definitely is not A. Definitely is not B. I mean, A, if you look, 10 kilograms, no, that's way too much. These 10 to the negative 1 kilograms is equivalent to 100 grams, which is way too much. So A and B, even if you didn't want to do all these calculation, A and B will not even be an option. So now we are between C and D, and because you are estimating, so we cannot have an exact number, but definitely is not C, so the option will be D. Last problem. What is a reasonable estimate of the kinetic energy of an Olympic athlete is sprinting in a 100-meter race? All right, so We are going to start with by looking what the statement is saying. Kinetic energy, we need a formula. And an athlete, that's the mass that we are talking about. So here, and also gave the 100 meter, which is distance. Doesn't help that much because for kinetic energy, I need velocity. So for the mass, I can use the estimated value of a person, which is 70 kilograms. But how do I do velocity? That's tricky. So the estimated sprinting time is 10 seconds. How you know this? Well, now you know. 10 seconds. So how we are going to convert this information into velocity to replace in this formula? Very simple. Velocity is distance over time. So the distance was given, which is 100 meters, and time is the estimated sprinting time is 10 seconds. So the velocity is 10 meters per second. Bingo. Now we can replace everything and calculate the kinetic energy, which is 3,500 joules. So let's look at the option. It's not 400, it's not 40 joules, sorry. It's not 40, it's not 400, it's not 40,000. So it will be in the range of 4,000 joules. So in this problem, you might be a little bit stuck with that sprinting time, how you're going to figure out the sprinting time. So 10 seconds is considered a standard. So this is all for this video 1 about physical quantities and estimation. And thank you so much for watching.